All right, good evening, everyone. We are now recording, and it looks like the sound is working. So I'll start out by saying I almost made it through double checking all of the exams. I didn't quite. I probably will actually make it through later tonight. So apologies for not having it quite back to you yet, but it is forthcoming immediately, and I will maybe announce for next week a review session where I'll go over and review all of it, because there were a number of questions with some widespread confusion about the on the exam. So I would like to give everyone a chance to see those few questions and come to understand them. I also, by later tonight, will post the final assignment, but I'll start out by giving you just a summary of the way it's going to work here tonight. What I'm going to do is post, I'll post the instructions, but the basic idea of the final project is I'm going to give you a real-life data set from the New York City Health and Behavioral Risk Survey, and give you a suggested topic that you can analyze with respect to this data set. But you'll be by no means restrained to doing this analysis around this data set, just so that you'll have something to fall back on. You will be welcomed and encouraged either to explore other analyses with this data set, or with another publicly available data set, or with a data set of your own from work. But the idea of the project will be to produce a poster presentation that we're going to have here on the last day of classes. And I'll bring in some easels where you can set up a poster. It's not going to have to be actually printed out like a big poster. Most likely and more affordably, you can just print it out on a set of regular letter-sized paper, and you'll be able to pin it up onto a board and present it. Everyone will come in person on that class, and we'll take turns. You'll have a few minutes to summarize your poster, to tell people what you did, both just a bit about the background, what analyses you did, what the results and the conclusions were. And we'll go through, and everyone will have their few minutes to present their poster. During the next several weeks before they are due, I will put interim deadlines for you to do certain parts of the project. I'm not going to grade these interim parts, but I will set up a discussion board on Blackboard, and I will ask that you post the different parts of your assignment there by these deadlines as a way to keep you on track and to get peer feedback, and I will also take a look through and provide a little bit of feedback, at least to those. It's important that you follow those deadlines and provide some feedback to your classmates. That will be the best basis I have on which to grade participation in the course. It's because I can quantify it. There will be a record of it on Blackboard, so please do that. And it's also, I think, in my experience, very helpful to you as well, not to save the project until the night before it's due and then try to produce a poster. So it's a fun project. It's way more fun than a final exam. I've done final exams before in this class, and I've done the projects and poster presentations, and I think everyone enjoys the project and poster presentations more. It's both a chance to do something a little bit more realistic than an exam. You won't be under the usual time pressures of an exam. And it'll also be a chance for you to, to do something out of the ordinary too, and to, a chance to shine a bit and show what your interests are and show everyone in the class the kinds of things you are interested in, want to do, and take from this class. There will be prizes. I'll just let you know in advance. I'm still working on procuring the prizes, but I take them seriously, and we will have voting on the prizes. So there will be several categories, and at the end I'll give everyone little sheets to keep track of all of the presentations, because you will see presentations for every poster. Take notes. In the end, vote on your favorites under the 3 categories, and then I will hand out prizes based on the people's choice, and you'll get credit for this. So lots of fun. One other thing to note about it: our last class is very late. It's, I forget, December 22nd, something like this. If you really don't want to be there that late, and this is what is keeping you from going home to your families or something like that, I will also provide the option of presenting a week before that. So I'll set aside some time in our last lecture and the week before the presentation, so that you can so that a few people can go early. It helps us out with the timing on the last day, and it might help a few people out in getting home for the holidays. Just occurred to me, I don't need to be screen sharing for this. I'll stop my screen sharing temporarily. Are there any questions about final assignment, about anything else? Yes.
Are we going to have to run like regressions or anything?
So question is, will you have to run regressions? The assignment should demonstrate competencies that we have covered in this course. So regression is one of the competencies that you've covered. You do not necessarily have to do regression. But the assignment that is assigned is designed to demonstrate several of the statistical competencies that we've covered in the course. And if you are doing an alternative project with your own data, it should also involve some of the competencies from the course. It wouldn't be a bad idea to send me an email just to check if the assignment that you're interested in doing meets the requirements of the final project. In the past, I have said, I think I've said that looks great, maybe every time, if not every time, almost every time. But the only thing maybe to watch out for is if somehow it is a project that is not involving much in the way of statistics, then I might be concerned about it. But in general, we have a number of different hypotheses testing besides regression. We have the tests on 1 and 2 means. We have analysis of variance that we're doing today. There is categorical variable analysis from next week, and then there is regression, which is in the final week. So it doesn't have to be regression. In general, there should be some descriptive statistics in the form of probably a table, possibly some graphs, and there should be some other analysis besides the descriptive statistics. Any other questions? All right, great. Let's as the semester goes on, I get more and more confused about which lecture and which week we were in, and I think Tony was confused about which week it was this week too. I had to actually refer back to the syllabus to make sure that this is in fact week 11 on the syllabus. Week 10 was the exam last week, so I'm now putting both on the slides. This is lecture number 9 on week number 11, I think. So we're going to cover power size and power analysis and sample size tonight. That's the important thing, that we're covering the right topic. Power analysis and sample size calculations covered in chapter 4 of your textbook, and analysis of variances covered in chapter 5 of your textbook. I'm going to start again with a quick review of hypothesis testing and power. Recall this handy chart which compares the true state of nature, the thing that we don't know, such as what the true population mean is, and the result of our test, which is rejecting or failing to reject the null hypothesis, which is a hypothesis about that true state of nature that we don't know. And in the case of the null hypothesis being true, then if we reject it instead, that is type 1 error, and that's the thing that we control with alpha, that is related to the p-value and the type of error that we're controlling with our hypothesis tests. On the other hand, if the null hypothesis is false, so it should be rejected, but we do not reject it, that is the type 2 error. And that probability is sometimes assigned the Greek letter beta instead of alpha. This is a false negative, but the related item that we usually refer to is the power, where when the null hypothesis is false, it is our power to reject that false null hypothesis. The power is 1 minus beta. So if you have a probability of making a type 2 error of beta, then your power is 1 minus beta. No, not here. Did you, Tony?
What's that?
What's that?
I'm sorry, what was that?
Did you call for help?
No.
No. Got a phone call. Huh, sorry about that. Yeah. All of these various aspects of the population and of experimental design impact this power. For example, increasing the sample size results in increased power. So for all other things being held constant, if the true difference between our population of the null hypothesis and the population of the alternative hypothesis is fixed, then if you increase the sample size, you have increased power to observe that difference. And that is because the standard error is equal to the standard deviation over square root of n. So as n increases, that standard error decreases. By the way, one of the things that there seemed to be widespread confusion on the test is how to formulate your null and alternative hypotheses. And so I just want to be clear that the null and alternative hypotheses, they're hypotheses about a population, not about a sample, right? Your sample is you use as evidence for or against the null hypothesis, but your null hypothesis is always about a population. And that population that it's about, we call the study population. And it is usually being compared to some other population in the null hypothesis. So on the other hand, everything being held constant, but if you have a less variable population, so a decreased sigma, this also results in an increased power. So there's less variability in the population or a higher sample size. It results in a smaller standard error. It means there's less variability in your sample means, so any deviation of your sample mean from what you expect under the null hypothesis becomes stronger evidence to reject the null hypothesis. All else being held constant, but if you increase alpha, you are more willing to accept type 1 errors. This is going to increase your power because given the very same p-value, you might reject the null hypothesis just by increasing alpha. So you have a higher probability of rejecting your null hypothesis. And finally, the greater the true difference between the means or whatever you are studying between your population for the null hypothesis and the mean for your alternative hypothesis, the greater that true difference, the more able you are to see it and the greater power you have to detect that difference. This word power is really a great term for what this is. It describes exactly what it is. It is, given the state of nature as it is and the study that you have designed, it is your power to detect a true difference if one exists. Why do we do power and sample size estimation? Let's talk about it from an example. If researchers were planning a clinical trial to measure the effectiveness of a pain reliever in reducing self-reported pain due to migraines, they have an estimate from previous studies of the natural variability of self-reported pain and some consensus or idea about how big of an improvement would be clinically relevant. This is something that is not coming from the data, but it is coming from a theoretical or a clinical argument about what size of a change is worth observing. Then they would like to go to their biostatistician and ask, how many patients do I need to enroll in a study in order to detect this with a type 1 error, a fixed type 1 error rate, and a certain power to detect that difference. And so this, this is a case where more specimens is not really your objective. I mean, it's always nice to have more data, but collecting more data costs money and it takes more time. And so the motivation for doing a power and sample size calculation is to have a study that is adequate for your purposes, but not overkill. The same way that an engineer designing a bridge wants to make sure that the bridge is strong enough, but they don't want to double the cost for no reason. You want it good enough, you don't want it to fail, but you don't want to go overboard and waste money. And this is also part of why very often in clinical trials, if they've been well designed, you're not going to have a p-value often of like 0.0001. It's going to be a bit more marginal because the study has been designed to be just powerful enough for what they want to observe. Because these can be really expensive, doubling the size of a study. The idea is quite different from what we've been talking about in hypothesis testing, because in hypothesis testing, you all know by now, right, that we start by assuming that the null hypothesis is true. And under that assumption that the null hypothesis is true, we calculate what is the probability of the sample that we observed or something more extreme. So it starts with that assumption that the null hypothesis is true. For power calculations, you do the opposite. You start by assuming that the alternative hypothesis is true, and then continue to calculate the probability of rejecting the null hypothesis in the future when we perform this hypothesis test. So it's I think, an important it helps to understand both of these a lot if you remember that you are starting with an assumption. You know, maybe this hypothesis testing assumption is even more unintuitive because usually you start doing a study maybe thinking that the alternative hypothesis is true. You do it because you think there is an effect there, but you're starting out assuming that there's no effect, that your study hypothesis is wrong, and you calculate the probability of what you're doing under that assumption that there's nothing to see. Whereas with power and sample size estimation, and you'll see in practice how exactly we do this, you start out by taking an alternative hypothesis and assuming that that is true. Here's an example. So I'm going to start with an assumption of the null distribution. So this is the distribution of something, our sample mean in this case. The distribution, well, a distribution of the test statistics if the null distribution is true. And this is a little funny. Now I'm drawing an alternative distribution that is actually the same, where there's no difference here. So it's not really an alternative distribution, but it's just to show you that in this case, the rejection region is the same for both of these. But here's where you can start to see how power and sample size estimation works. So under our null distribution, this is a standard normal distribution where I'm drawing a line at 1.96, where the rejection region, just showing on the right-hand side here, of 0.025% of the area is above 1.96. But if this alternative distribution is true, it has the same standard deviation, but it has a mean of 1, then the probability of observing something, a z statistic above 1.96, is actually much greater than 0.025. It's 0.169, 16.9%. So in this case, because the alternative distribution is true, or if we make the assumption that it's true, then the probability of being up above, of observing a z statistic above 1.96 is going to be greater than 2.5%. And that would be the power. This is still lousy power, 17%. So this would be an example of an underpowered study. If we were interested in a difference in means between the null and alternative distribution of 1, we would have only a 17% chance of observing it here. And you'll notice I'm ignoring something here, the left-hand tail. That is because under this alternative distribution, the probability of having a value less than 1.96 is pretty negligible. It's not 0, but it doesn't actually add anything to this power to 3 decimal places. So, so I'm just not drawing it there because it's infinitesimal. So let's see, we had here only a sample size of 1. Now, if I increase this to a sample size of 10, the standard error starts shrinking. And so with the same mean of 1, now my probability of having a z-score above this rejection region is, so it's not at 1.96 anymore because the this is this the sampling distribution, and with it, it's what is its standard deviation going to be? It's going to be it was 1, now it's 1 over the square root of 10 is the standard deviation of the sampling distribution. Now, the rejection region is to the right of, I don't know, someone want to check that? Fact check me? I hope I'm right, that if you go 1.9, let's see. So it would be 1.96 over the square root of 10 would be the rejection region. So both of these, the sampling distribution, if the null is true and if the alternative now have a smaller standard error. Good, you're checking me? I wonder if I can pull up the calculator here. I want to keep myself honest.
1.96
Over the square root of 10?
0.619.
Okay. So now, if the null distribution is true, then our rejection, well, let me put it this way. We're going to work under the assumption that the alternative distribution is true, but we know that in the future, when we go ahead and do this test, we're going to be performing our standard null hypothesis significance test. And under that significance test, we're going to use a mean of 0 and the standard error, which is 1 over the square root of 10. And we know that we're going to reject the null hypothesis if we get a z-score of greater than 0.62 or less than minus 0.62. But to do our power analysis, we're going to assume that this alternative distribution is the correct one. And using that assumption, calculate what the probability of getting a z-score more than 0.62 is. Give that a moment to sink in. Any questions about that? This interpretation is important. The idea that when you do a power analysis, it is based on an assumption of a true alternative hypothesis, but where you haven't yet done your null hypothesis test. It's not something that you do after the fact, like using the mean and the standard deviation calculated from your study. It's something that is part of study design. I have been asked by reviewers to do a power calculation for the p-value that wasn't significant, and you really have to think hard about how you interpret that. You have to interpret it in terms of doing a future study. So I'll continue. If this difference in means is 2, n equals 10, the null distribution is unchanged, right? But this alternative distribution, the one that we're assuming is true, is shifted all the way over to 2, and there's almost no probability that we're going to observe get a z-score of less than the rejection region of 0.62. So this has a power of 100%. This is, in fact, an overpowered study. Yes?
So we still kind of are utilizing the null, like the null distribution is standard.
Yeah, because you're planning for the the null hypothesis significance test that you're going to do. So you know that when you go and do this significance test, it is against a z-score of 0 with rejection regions here of 0.62 and minus 0.62. So, so you know the test that you're going to do. You want to calculate the probability that you're going to reject that null hypothesis. And we're doing it under the assumption here that the truth is that H0 is false, and actually making an assumption not only that H0 is false, but by by how much the test statistic is different from that center of the null distribution. Is this any other questions? Yeah. Okay. So it is the most important thing right now is for you to understand these relationships between sample size, population variability, and differences in the null, the expected null test statistic, and or null population mean and mean under the alternative hypothesis. But in this case, with a normally distributed sampling distribution, you can calculate the power in a relatively straightforward way. This formula covers both means and proportions for one sample and for two samples. And I provide here a general formula involving difference over the standard error of that difference. This part here is sometimes referred to as a relative effect size. It is, this difference is the effect size. It's how, like if you're talking about a treatment for, for pain relief on a score from 1 to 10, the effect size is how much the treatment changes the mean pain score, or how many hours of sleep a sleep aid increases your sleep by. And that it is divided by the standard error on that difference makes it a relative effect size. So what matters for the purpose of power calculation is that relative effect size, the ratio of these two things, which is unitless. So regardless of whether it's hours or a score, this relative effect size is meaningless, or sorry, is unitless, not meaningless. Freudian slip there. No. So the only difference between these 4 different applications is the way that you calculate this standard error of the difference. And you've learned all of these so far. These are going back to the hypothesis tests for normal distributions, on means, and on proportions under the large sample size assumption. And this z alpha over 2 is just the this rejection region that's shown on here. So for a standard error of 0.316, it is 0.619. It's the value of the z statistic at the rejection region. I'm going to give you these equations so that you have them on hand, but also tell you that the main reason that I'm giving them to you is so you can see what the ratios are and what increases. So the previous one was a calculation of power, that probability of rejecting the null hypothesis under the assumption that the alternative is true. And this is for sample size, so a reverse calculation. And I'm giving it to you not so much because I expect you will probably use it. You can very easily go to a web page and do this calculation, or do it within any statistical software. But it's nice you should have an intuitive understanding and recollection of how these things relate to each other. So this is telling you for a given population standard deviation, for the z-score for your power, and for alpha over 2, type 1 error, it increases with the square of both of these things and decreases with the square of that difference. So it's still this delta over sigma. Can you remember what I called that? I gave it a name on the slide before. I'll write it down here. I have a way to. It doesn't allow me to type. Delta over sigma was the relative effect size. So for here, it was, this is delta over sigma. And for n, it's an inverse of that, a sigma over delta, but it still involves that relative effect size. So in general, the more variability there is in the population, the larger a sample size you're going to need to observe a difference between two populations. That makes sense, right? And in general, the larger the difference between those populations, the smaller a sample you can get away with having. You know, if a treatment is very, very effective, you don't need to observe as many people to see that effect. But if the natural variation of people receiving the same treatment or receiving a placebo is very large, you're going to need more people to observe the same effect. Okay. It's essentially the same, like on the previous page for calculating the power. It is essentially the same calculation for proportions, except you have this different formula for calculating the standard deviation, that square root of 2 times p times 1 minus p. But this is, again, just still, this part is just, this is a sigma squared over delta squared. There. As a note, this n that we are calculating here is the sample size in each group. And if you use software or a web page, it should be very clear about exactly what this n means. Does it mean your total sample size for the study, or does it mean the size for each group? In this case, it's for each group, assuming equal-sized groups. if you were, for some reason, having to have different sized groups, it's going to be your smaller group that will limit your power more so than the big group. In general, if you have very unequal sample sizes in a two sample test, you're going to continue being limited by the smaller group. And as I mentioned, this Z beta refers to the power, and typically you do this estimation for wanting 80% power or 90% power. It's not as widely agreed on as an alpha of 0.05. But this is the value of Z corresponding to a probability of 80% to the left of that, like on the pictures that I was showing on the previous page. The area to the left of this value of Z is equal to 80%. And under this desired level of statistical significance, typically 1.96. Here it's 1.96 because the standard error is included in this calculation. So this Z in the examples before wouldn't go down to the 0.6 or whatever. This is just 1.96, and this is, Z of 0.025, which is 1.96, and this is the Z for 0.8. So, if you are given, there are four different population parameters or study values, delta being related to the populations, alpha, beta, and N being related to your study. In general, if you're given any three of those things, you can calculate the fourth. And the way these are implemented in any of the software is generally you just go ahead and specify any three of these, and it will return to you the fourth. And so they're also included together, power and sample size estimation, for that reason. It's really the same formula. It's just rearranged different ways to solve for different values in that formula. And this is something, if you are a biostatistician, you'll find that you do a lot of these power and sample size calculation, because if someone is starting a study or applying for a grant, it's frequently something that they have to do. Unfortunately, it's often not as simple as the ones that we've learned here. There is some kind of complication in the study design, but this gives you a start. So this is just a summary of the things that I mentioned for that formula. Ways that you can increase power are by increasing the size of the effect. If the difference between your null and your alternative means is larger, you have greater power to detect them. And alternatively, the smaller the difference is, or the smaller the difference you want to have a power to detect, then you will lower your power unless you adjust some other aspect of your study design. So this size of the effect and this the sample size and the significance, these are things that, that you will set yourself in that study design phase. The standard deviation of the characteristic is something that you would usually try to get from preliminary data or from other published data. You would need to have some kind of estimate of the natural variability. The other three, this effect size is usually based on what you consider worth trying to detect. Then alpha is something that you're planning for, and sample size or power is something that also that you are planning for. Any questions about sample size before we move on? Tony has some very nice examples of sample size in the lab and power calculations that may help make it clearer.
I'm searching for some sites.
What's that?
I'm searching for some sites and find some calculators.
Yeah. Did I put the URL for this calculator? I liked. I didn't put in the URL. I can dig that one up. But this one I liked because it was. Oh, you know why? This is because this is from a package in R. This is not actually from a website.
I'm having some trouble finding them that are on the machine because they want a version Java that I'm not running.
Yeah, it's helpful having an interactive power and sample size calculator where you can just adjust the sample size or the alpha or the standard deviation and see the effect on power or vice versa. As an aside, maybe I'll just mention that the power size calculations often do get more complicated than this when it's for some other kind of study with, I don't know, just with a more complex design. Sometimes you can do those power calculations just with your software. Like I know in R there are power size and power and sample size estimators for a lot of different study designs. But when you're really stuck and you don't know how to do the sample size calculation, you can actually do it through simulations. And the simulation, when I first did one of these, it made it really clear to me how this was and or exactly how this worked. And I wish SPSS were better for doing simulations because we would have you do it. But when you do this simulation, you just go through exactly the steps that I described. You start by with an assumption about what the true alternative distribution is. You just define that and you start drawing samples from this alternative distribution. And then for each one of those samples, you go through and you perform your significance test, your t-test, your z-test, whatever it is. It can be however complicated. You get a p-value. If it is less than 0.05 or whatever alpha you chose, you reject your null hypothesis, and then you just count them up and calculate how many times out of 100 you reject your null hypothesis, and that's your power. So like the simulation is actually way simpler than various calculations, and you can use a simulation every time as long as you're able to draw random samples from your true alternative distribution, and then go through with the significance test that you're planning. To me, it's amazing how that works. Of just you know, going through like a simulated entire study of drawing a sample, calculating the test statistic, and performing your null distribution, and then using that directly to calculate your power. I think it's great. Okay. So lots of stuff we're covering today. I'm going to introduce to you analysis of variance for comparing the means of 3 or more groups. And I'll cover the assumptions of such tests and carry out a hypothesis test where our null hypothesis is that several populations means are equal. Go through the one-way analysis of variance table and talk about so-called post hoc tests. Going back to this cell phone study, remember the study was that we recruited volunteers and we had a control group doing a driving test where they were suddenly given a red light and had to hit the brakes at random times, and a treatment group or alternative group that was told to talk on the cell phone while they're doing the same driving tests and hit the brakes after they see a red. And for I think there were 30 volunteers in each group, we measured the response time to those red lights was measured for each of them. And then we performed a test against the null hypothesis that the mean response times for those two populations, the control and the cell phone group, are the same, and an alternative that they are different. Now, suppose that instead of just a control on a cell phone, we have two different groups, one that is using voice only and another one that is using voice plus SMS or text messaging, so they have data on their phone as well. And so we have 3 groups now instead of just 2. And in this instance, our global null hypothesis will be that there is no difference between any of these 3 groups, and that is what we will test by analysis of variance. And secondary follow-up question will be, okay, if there is a difference, where does it lie? Is it that both of the voice and the voice plus data groups have a different mean response time than the control group, or is it, are there only, is only one of them different, and is there a difference between the voice only and the voice plus data? Does using data make response time even slower than just using voice? Another example, in the evaluation of several different training programs to complete a learning task. Same idea, if we have 3 different groups and observations for the groups that have these 3 different methods applied to them. In this case, the null hypothesis is that these 3 training programs are equivalent. There's no difference in the observation, in the mean observation time of populations, given these 3 different training programs. So this was obviously a very small study here in this second example. Only 3 observations in each of the groups. But I'm making an SPSS descriptives table for this imaginary study that I showed the data for on the previous page. And here the 3 methods have means of 12, 10, and 22 standard deviations. So the variability of learning times within each of those groups is 3.6, 2.6, and 3.6. So just off the bat, looking at this, it looks to me like the difference in means of 2 here is not very big compared to the standard deviation. So of course the standard error is going to be smaller than this. It'll be 3.6 over the square root of 3, but even that's 3.6 over 1.73, that's still about 2. The standard error is going to be. So the standard error is fairly large relative to the observed difference in means. Doesn't look like that big of a difference in means. But this, on the other hand, 22 is quite different. So this is unscientific, just taking a look, but it looks like maybe method 3 is a worse method than methods 1 and 2, because the completion time after that is quite a bit slower. It's a little easier to see with a box plot here. Here's the method 3 that looks like a lousy method. But without doing a hypothesis test, maybe this is an amount of variability that just taking 3 people, a different 3 people, will by chance have this different a distribution than another 3. Could happen. But why don't we just use t-tests? One reason is that you would have to do 3 tests, and that's not necessarily a bad thing, as long as you're aware that each of those tests has a 5% type 1 error rate. So by the time you do 3 of them, your chances, if all your null hypotheses are true, your chances of rejecting one of them is going to be more than 5%. So you're no longer controlling your type 1 error rate at 5%. It is possible to control that type 1 error rate. There is a correction that we'll cover called the Bonferroni correction that controls the overall family-wise type 1 error rate. But that would not be as powerful a test as what we're going to cover, which is a single test with a 5% risk of type 1 error overall, the analysis of variance. So we're using the one-way analysis of variance to compare the means between 2 or more populations. And I say 2 because you actually can use it with only 2 in place of a t-test and get equivalent results. But it's extendable to more than 2 populations. Just to write down here these problems with using the multiple t-tests. This is not, I want to say, this inflation of alpha over multiple comparisons is not a fatal flaw because it can be corrected for. It's an issue. It's not a fatal flaw. It's not the primary reason that you would want to use analysis of variance in this case. The primary reason, so if you are not aware of that and just do 3 t-tests, you're going to end up with a probability of making at least one type error of 14% instead of 5% without any correction. But analysis of variance is a really an ideal test for this scenario, for having one test to test the global null hypothesis of the means of several groups all being equal. And the basic idea is, similarly to a t-test or a z-test, that a differences between groups that is not that big compared to the variability is hard to discern from sampling variation. Whereas if the difference between the means of groups is fairly large relative to the variability within the groups, that's less likely to happen due to random sampling variation. So in this example, the group means or medians are the same, but the variabilities are less in this on the right. So this is something that would be less likely to happen as a result of sampling variation, this size of the differences in means. The same thing drawn as a graph here. This is two groups. Just like the 1 and 2 that we saw, the variability is it's the X files. Doesn't take me too many bars to recognize that. So in this example of the three training groups, we had 2 with a fairly small difference in the means, and a third one with a fairly large difference in the means. And just by looking at this, again, just like when we looked at that third one, you can see that, okay, if you keep on drawing samples of size 3 from these 2 distributions, you're going to get some variability in the means. Probably you're not going to get a sampling variability in the means like this very frequently. It will happen, but not as often. Oops, looks like I lost something on the slide here. This should say, this is just reminding you of the terminology. This is x1 bar, x2 bar. And I'm putting this in again here just because I know that even after we've been doing this for a while, that there always still is some confusion about the fact that that what we observe is something from a sample, but what our hypotheses are something about a population. Our hypotheses in this case are about several population means, but our observations are about several samples from these hypothetical populations. Oops, sorry, that should not be a mu, that should be an X bar. G being the number of groups. So recall our null and alternative hypotheses for one population, for 2 populations, as we've done already. For multiple populations that we're generalizing to now, the null hypothesis is that all of the means in those populations, whether it is response time or time to complete a task, is that they're all equal. And the alternative is that they are not all identical, but at least one of the population means is different from the rest, or possibly there is more than one difference. As always, any hypothesis test you do, there are assumptions involved, and I want you to know what the assumptions are. Provide a nicely searchable slide so you can find assumptions for any lecture. First assumption is again that the data are approximately normally distributed, or that the sample size, if the sample size is large, this becomes less important. It is worth keeping in mind that ANOVA is both robust and conservative to violations of this assumption. So robust means that it's not too sensitive to violations from normally distributed populations. And conservative means that if there's a violation, it will tend to increase your p-value. It'll reduce the power of your test, make you less likely to reject the null. So it's not likely to cause you to make false claims. So it's robust and conservative. A few rules of thumb here: that the one-way ANOVA with 3 groups is generally safe. If you have small sample size, your total N1 plus N2 plus N3 is less than 15. If you have well-behaved data, it's symmetric, there are no outliers. Up to 40, it's still safe if you have moderately skewed data, not too many outliers, no more than 3. And if you're over 40, then it's pretty robust, even to skewed data and outliers. Not an exact measure, but sort of a rule of thumb. It depends too on whether, how, if these are all the same or one of them has only a sample size of 2, but this gives you a general idea. The second assumption is homoscedasticity. So unlike the t-test where I gave you options for assuming equal standard deviations and another option for keeping them separate, we make the assumption here of equal standard deviations. That's called homoscedasticity. I do not recommend hypothesis tests for this assumption of equal standard deviation. And the reason is that what's going to happen for this, so you have some test where your null hypothesis is that all of the groups have equal standard deviation. What's going to happen to the power of that test the larger your sample size gets, based on what you learned earlier today? Yeah, anytime, no matter what test you're doing, if you have a larger sample size, your power increases. Very general rule. So the larger your sample size, the greater power your test of equal standard deviations has. What happens to your ANOVA and its robustness to violations of this as sample size increases? Just from the very slide before this one. So let's say we go up to a total sample size of 200. What did I say about the robustness of the analysis of variance?
Does it matter as much? Over 40?
Yeah, it's generally safe even with skewed data and outliers. So the larger the sample size gets, the more likely you are to reject the null hypothesis on some test of standard deviations, but the less it matters. So for that reason, it's just not very useful using a hypothesis test here. There are, sorry, the name is escaping me, diagnostic plots that you can use for assessing these. They're a better way to do it than hypothesis tests. I remember that, one of my early statistics textbooks that said that performing this Bartlett's test before doing an ANOVA was a little bit like sending a rowing skiff out on the ocean to see if it was safe for an ocean liner. So, but I just mention it because it's something you might hear, and this is the reason I don't recommend it. As another rule of thumb, if your observed sample standard deviations don't differ by more than a factor of 2, then your assumption of homoscedasticity is fine. But again, ANOVA is conservative when this is violated. So if anything, you are less likely to reject the null hypothesis. As with every other test we have done, there is an assumption of statistically independent observations, so that the sample is randomly drawn from these G different populations, that each of those samples is a statistically random sample. In a survey, that those samples are randomly drawn, or in an experiment that subjects are randomly assigned to those groups. But the point being that, that we have a statistically random sample. So in order to perform an ANOVA, there are these two different variances that we calculate. Remember, ANOVA stands for Analysis of Variance. Well, there are two different variances that we calculate. One is the so-called within group variances. So this is the variability of individuals within each group. So like I was saying, that the probability of observing some difference in means depends both on the difference between the groups and the variability within the groups. Well, we need this estimate of the variability within groups. And this calculation is essentially, it is a weighted mean of the standard deviations within each group. So S1 is the variability, is the standard deviation of sample 1. And it is weighted by the number of degrees of freedom of group 1, which is N1 minus 1. So we just continue that for each group. It's the standard deviation of each group times its degrees of freedom divided by the total sample size minus the total degrees of freedom that have been subtracted off here. It's just a weighted within group standard deviation, or within group variance. The second variance is the between group variance. And this is calculated in a similar way, except that it is the variance of the group means. So instead of it being the variability of the individuals within each group, x1 bar is the mean of group 1. So I'm taking the mean of group 1 minus the overall mean, and weighting that by the sample size, by n for group 1. And there's no n minus 1 here because this is a set of group means, and our correction for the degrees of freedom is just on the denominator here. So we've got an estimate of the between group variance and the within group variance. What would be like the easiest possible way you can think of to compare these two variances? We want a test statistic that that is going to be high when the between group variance is high and the within group variance is low, and we want something that will be smaller when they're very similar. So if we have a bunch of groups that look like this, we want a small test statistic. If we have groups that are really different like this, we want a large test statistic. So I don't know, who has a guess of what would be a test statistic? Any test statistic that has that property of increasing when the between group variance becomes much larger than the within group variance. you have your chance to invent a test statistic, but it's only going to last for another 15 seconds. Let's have a guess. You have a guess.
I see the answer, so it'd be cheating.
Yeah, that's cheating.
And
But I'll take cheating now.
Even if I didn't see it, I would say some type of proportion.
Yeah, proportion. You know, just like we were using a proportion before of the relative effect size, which was like, you know, the difference in means divided by the variability in the difference. So what about a proportion that is just the between group variance divided by the within group variance? That's something that is going to increase the more of a difference there is between those. And that's the F statistic. And that is the statistic that you use for analysis of variance. So this between group standard deviation and variance, again, is the variation in the group means around the overall of the grand mean, and the within groups standard deviation, variability of the individual observations around the group means. And that statistic is just the ratio of these two variances. I mean, I ask because to me it's kind of amazing that that's all the F statistic is. You know, I think, yeah, if you just sat down and someone forced you to write down something that would increase when the between group variance was more than the within group variance, that might be the thing that you wrote down. There are probably other things you might, but it's a pretty intuitive choice. So the calculation of the SF statistic is pretty straightforward. You have all of the formulas that you need already. But to get a p-value and perform your significance test, you need the distribution of F. And we've gone to increasingly more complex distributions in this course, starting from the Z statistic that the standard normal distribution, there's only one of them, to the T distribution that depends on the degrees of freedom. There's one for each number of degrees of freedom from 1 on upwards. And now the F statistic has a distribution that depends on both the numerator and the denominator degrees of freedom. So for every different value for the number of groups minus 1, or the total sample size minus the number of groups, there's a different F distribution. It's still the same idea, it's just there are more of these F distributions. It does differ from the Z-test and the T-test, and is more simpler than them because even though we have these 2 degrees of freedom now, it is only a one-tailed test. Even though it is inherently, there's no, it's not a one-sided alternative hypothesis. It's always for analysis of variance. All of those equalities are just inequalities under the alternative hypothesis. So even though it's a 2-sided test, it's a one-tailed distribution. Because no matter how you have departures from the null hypothesis, it only ever increases the F statistic. Anytime you have a group with a mean that is different than the rest, it will increase your F statistic, whether that mean is greater or less than the other means. So rather than having to do the like alpha over 2 stuff that we did for the z and the t-tests, all we need is to look at the area under one tail of the distribution. And the p-value is the probability only of having an F statistic greater than the given alpha, or the F statistic that we observe. Going back to this training programs example with the 2 groups that had fairly similar medians and the one that was fairly different, I've drawn on here the grand mean. This is the mean of all 9 observations, so that you can see on here the between groups variance. So whereas the within groups variance are calculated, they're sort of equivalent to the width of these boxes, the between group variances are the mean, each of the means minus this grand mean. And here you can see that this third one has a larger deviation from the grand mean than the other 2 do. So in this case, the sample sizes are equal, so the within group will be an average of these 3 within group variances, and the between group will be the average of these 3 deviances. And when you do ANOVA, while you're listening to ambulances, you will always see a table something like this, and you're going to get pretty used to tables like this, because ANOVA is useful for, it turns out, not only this simple case of the one-way ANOVA with multiple group means, but also for any kind of regression problem. You can do an analysis of variance for assessing statistical significance of all kinds of regression models. And in all of these cases, it is possible to produce an analysis of variance table that looks something like this, where you see the sum of squares for the between groups and the within groups comparisons. This will get to have more groups once you get into doing this for multiple regression. Degrees of freedom for each of for the numerator and the denominator, because that affects the F statistic. The mean sum of squares, just the sum of squares divided by the degrees of freedom, and then an F statistic that is a ratio of these two mean squares. So here, 124 divided by 11 should be 11.273. And then this significance, the p-value, would be the probability of observing an F statistic of 11.273 or greater, assuming that the null hypothesis is true, and this sample is coming from a sampling distribution of F statistics with 2 numerator degrees of freedom and 6 denominator degrees of freedom. Are you checking? Keeping me honest here, doing the fact checking? Is 124 divided by 11 equal to 11.27? I'm pretty sure it is. So this p-value of 0.009, assuming we're using an alpha of 0.05, would lead us to reject the null hypothesis and accept the alternative that at least one of these methods is different, but it doesn't tell us which. It just tells us that that between group variance is larger than the within group variance. And that's where these so-called post hoc tests come in. Post hoc tests are a set of pairwise tests that we do. In the case of Way ANOVA, there are a series of pairwise t-tests that we do only after rejecting the f-test. So we found that there is some difference in between at least two groups, and we want to know where it is. We do not do this if the f-test is not significant, because if there were some difference between these groups, we would have discovered it from the ANOVA. But the nice thing about doing post hoc tests after doing an ANOVA is that you know already that you have evidence for rejecting this global null hypothesis. So you believe at this point that there are some differences between the groups. And so you can go ahead and do these pairwise tests, and at least the one that is the most different, feel reasonably confident that that is a real difference. There are a few different methods you can choose from when doing these post hoc tests. The standard one is this so-called Tukey method, sort of a default. You don't have a reason to choose anything else, which is the best just for doing all pairwise comparisons. And alternative is this Bonferroni method that is also not just for all pairwise comparisons, but for any pre-selected set of pairwise comparisons. So if you decide in advance that you want to test not all but some of the contrasts, the Bonferroni method would have you perform those contrasts, calculate p-values, and multiply those p-values by the number of tests that you do. And this can be applied to any pre-planned contrasts, as long as they're not selected based on your data. So if you decide to select your top two contrasts because those two looked the biggest based on your data, then the Bonferroni correction is not going to help you to control your type 1 error rate anymore. A couple other ones worth mentioning. This Dunnett method is for comparing all treatments versus one control, and the Sue method is for comparing the best versus all others based on the data. So in the Dunnett is also pre-planned. Sue is actually based on your data and picking the picking your one extreme against all others. So if in this case you wanted to test group 3 against all others, you could use the Sue method. Microtime. Boy, we're getting a little bit late here, but I'm almost done. Let's see. Oops, sorry. This is referring to the Tukey method, and it will make more sense when you see an example of it when you're performing something. But in the Tukey method, you plot confidence intervals on the difference between pairs of means. So similarly to like you've done in the two-sample t-tests, you didn't make two different confidence intervals for each sample. You made a confidence interval on the difference. And when you do this Tukey method, you'll see a set of confidence intervals on each of your pairs of means, and if and they're corrected in a way that they're valid for multiple testing, so that if you see they're bigger than they would be if you were only comparing two means, so that if any of them, that confidence interval doesn't cross the zero difference, then you have evidence that that pair that has a difference in their means, or that pair of population is different in their means. So this is an example of the Tukey. I think that stands for honest significant difference. Like honest, there's a significant difference. And you will see for each of these, the mean difference with a confidence, or these are just the two mean differences, standard errors, and a lower and upper bound on the difference in means. So this is the lower and upper bound for the difference between method 1 and method 2, and this is the lower and upper bound for the difference between method 1 and method 3. So for 3 methods, there are there are 6 different comparisons being done here. Although in terms of p-values, they will be equivalent whether you're comparing 1 to 2 or 2 to 1. Those are the same tests. So again, just to demonstrate, if you actually draw these out where the difference crosses 0, or where the confidence interval on the difference crosses 0, that's no evidence of a difference in means, and in these cases there is some evidence of a pairwise difference. So here we think there's probably not a difference between treatments 1 and 2, or groups 1 and 2, but there is between 1 and 3 and between 2 and 3. So to wrap up, you can use the t-test for this null hypothesis that a number of different groups have identical means. F-test is actually more general than that, and you will get greater use out of it once you learn multiple regression in BIOS 1. And like the chi-squared statistic, which we haven't actually covered yet, we'll cover that next class, it is right skewed, and it's always positive. And so we use only the right tail of the F distribution. Instead of the usual assumptions, we use post hoc tests only if the F test is significant. Any questions before we take a few minutes break and let Tony take over? All right, thank you very much.